right, we're back for 11.4 talking about normal distributions. A lot of what's in this part of the chapter we talked about last section because we needed to kind of know what a standard deviation was and what normal distributions were to be able to use that formula. So this is kind of like just going back and building on that or cementing that so you really understand what a normal distribution is. So that thing we've been talking about, which is how much data lies within one standard deviation or two standard deviations of the mean, is actually called the empirical rule, right? So that's the thing that tells you 68% of the data falls in with one standard deviation of the mean, 95% of the data falls in plus or minus 2 of the standard deviation of the mean, and then that 99.7 falls within plus or minus 3 standard deviations of the mean. And then this is saying 4 plus or minus 4 because if you go out one more, you have 100% of the data. Right, so all of this is there. We talked about it last time. It's all on page 573 if you want to look at it more. So remember that a normal distribution means that it's a perfect bell curve, right? A normal distribution means that the mean is right in the middle of the data and it equals the median, right? Those two are equal. So let's apply this empirical rule to these other sets of data here. So here it says an example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men exhibited an approximately normal distribution. Their chest circumferences ranged from 33 to 48. So that's where all the data fell, 33 to 48 inches. And the mean chest measurement was 40 inches. The standard deviation was 2. So let's use the empirical rule to understand this data. First, it asks us which chest measurements contain 68% of the data. Well, we know the mean. They told us the mean is 40, right? So this value, the mean, the middle is 40. And we know within one standard deviation, plus or minus 1 of the mean, we go to the left or the right, one standard deviation, we have 68% of the data. So the standard deviation was 2. So if we go to the right, it's plus 2. If we go to the left, it's minus 2. So we know that 68% of the data falls between 38 and 42 inches. So that's what we would write here. We would expect approximately 68% of men to have chest measurements between 38 and 42 inches. We're looking at this graph, we're looking at the statistics, and we are making this statement. So let's keep doing that. Now it says, what would you expect the chest measurements to be for the 2.5% of the men with the smallest chest measurements in the population? So if I come back and look at this, we know that 95% of the data fall within plus or minus 2, right? That means there's only 5% of the data left. So that means over here would be 2.5%. And on this side would be 2.5%, right? Because that's the only way we're going to add up to 100. So if they're asking us, if we go back, they're asking us this 2.5% of the men with the smallest chest measurement. So we start out with the mean. We go 1, 2 standard deviations over, and we only are focusing on the smallest, so this side of the bell curve. So we would expect approximately 2.5% of men to have a chest measurement less than 36 inches. We could go the other way and say we would expect approximately 2.5% of men to have a chest measurement more than 44 inches as well, right? But they asked us to focus on the small. All right, let's use another example about SAT scores. Recent SAT scores for college-bound seniors are normally distributed with the mean score 508. Okay, so normally distributed, check, we need to know that. The mean score in the middle here is 508. All right, there we go. Standard deviation is 121. So that means every time I go out one standard deviation, I'm adding or subtracting 121. That's how I get these numbers down here. And we need to use the empirical rule to understand the performance. First question. What proportion of students received scores between 387, here's 387, and 629? Well, if I look at that, those are both one standard deviation away. So I would say 68%, because that's what the empirical rule tells us, will be between 387 and 629. These SAT scores look quite low. I wonder if it's just the section, right? Like the math section. Oh, yeah, here, math scores. It's like, wait, these are very low scores. So you would, how does this help you? Just like we talked about before, if you scored a 600, you would say you're with the majority of like 68% of the people, right? Most people, you could see this as like a big chunk, right? Right here. And then if I go out, I'm at 750 within 2 standard deviations. And you're really like, if you scored here, you're in the top 2.5% of scores, right? If I take that out, if you scored 629 and up, what percent are you there, right? Well, we know that we'd have to calculate the percent value in each bracket, which is exactly what we're going to do actually. So that's how you can use it to see where you fell. So we're going to actually use what I just said to figure out this one, right? So it says what proportion of students received a score greater than 387. So how many kids, if that was a straight line, got above a 387? Well, one thing we know is that this middle part is 68%, and they said they figured out this is 16. But that's not even how you could have done it that way, right? But what I would have thought about it as is I would have said, well, first, I know that this part of the bell curve is 50%. And then I know that this section is half of 68, so that's 14. Or why did I write 14? That's 34. So then I could add those two, right? And I would say, well, we would expect 84% of students to receive a score higher than 387, right? I'm just using the empirical rule to split this up. So what if, let's just change this. What if I go back up to what I said here and you scored above a 629? What percentile are you in? Well, I know that this whole thing from here to the end is worth 50%, right? And then I'm taking this chunk off, and we know that chunk is worth 34%. So what is 50 minus 34? 16, right? So you know that if you scored above a 629, you're in the top 16% of scores. So you know you did pretty well, right? And that's how you can start thinking about why we have standard deviation, and it helps you get your percentile of things. Okay, so another way that you can compare your percentile or where you fall in relationship to the standard deviation, if you don't have the entire graph, right, is to use a z-score. So the z-score counts how many standard deviations a data value is above or below the mean, because it divides the difference from the mean by the distance of the standard deviation. So it says that you're usually using them for normal distributions, but you can use them with any distribution. So this is how you find the z-score. You want to write this down. You take your data value, whatever the value of that point is, take away the mean, and divide by the standard deviation. And it tells you, oh, I'm 2.6 standard deviations above the mean, or I'm 3.4 standard deviations below the mean. That's what the z-score will tell you. So let's try it out. So here are ACT and SAT scores, right? Two different assessments you can take in high school. And so someone wants to someone took the ACT, who's it? Ella took the SAT and she got a 1380. Alicia took the ACT and she got a 32. And they're trying to go, well, which score is actually better, right? Because they're two different assessments. So you can't just compare the raw score. So they're going to use a z-score. The mean SAT score is here. It's 1,000 and the standard deviation is 200. The mean ACT score is 21 and the standard deviation is 5. Who has the better score? So the quick way to do this is to find their z-score. So here's the formula. And you can see for Ella, she got a 1380 in her SAT. Take away the mean, divide by the standard deviation. So she scored 1.9 standard deviations above the mean. Where Alicia, she got a 32. Take away the mean, divide by the z-score of 5. That comes out to be 2.2. So she scored 2.2 standard deviations above the mean. So just looking at those, you can say Alicia's score is better than Ella's because she was in a higher percentile, right? She was more in the upper part of that normal distributed graph. So let's try this on this one problem. The weight of a captive adult female lowland gorilla is normally distributed with a mean of 82.3 kilograms and a standard deviation of 15.33 kilograms. So they've given us this gorilla named Sasha. What a coincidence, right? And to calculate Sasha's z-score. Okay, so we're just going to focus on that. So Sasha's z-score is going to be the weight, 61.8, take away the mean, 82.3, divided by the standard deviation. So it's approximately negative 1.34. So that means she's a little more, he or she, does it say female? She's a little less than the mean. She's a little more than one standard deviation away to the left of the mean. Okay, so that might mean she's falling in that underweight category. So you can find the percentile of that, right? So if this is where she is, negative 1.34, you're trying to figure out she's at the bottom what percent? Like, what does this percent equal? It's easy when it falls right on the line, but when it's 1.34, right, you have to do a little bit more math to figure it out. And so one thing you can do is, this is how you do it in a spreadsheet, which is what we want to focus on. So you would put in the z-score, norm.s.dist, parentheses, you put in the z-score, and then a 1. And it'll tell you that she's, what does it say? Oh, negative 1.34, put that, is approximately 9%. This means that about 9% of all captive adult female lowland gorillas have a weight less than or equal to Sasha's. So that's how you could transform your z-score into a percentile using a spreadsheet. Okay, that's it for today. I will see you next time. Bye-bye.